Swayam Prabha. Digital India. Educated India.
I will talk about something which is very, very basic and which all of you know. So, what I will talk is what are vectors? Okay. So, what are vectors? And when somebody says vector, then what do you mean? Okay. So, the standard definition of vector is something which has a magnitude and it has a direction, right? So, suppose you consider V, you can say that this has three components, Vx times x cape plus Vy, y cape plus Vz, z cape. Okay. What I will do is I will give you a new definition of vector, which will still satisfy this, but that will be helpful for us to define more general things, and it will also help us understanding some of the very basic principles of physics and then how to formulate them and so on and so forth. Let's say you consider the position vector. Okay, it's nothing but x ex, x times x cape plus y times y cape on a plane. Okay, I am not even going to 3 dimensions. I will just consider a plane, and then on this plane I will consider the position vector. So you have this is your x axis, this is your y axis, and then the position vector is something like this. This is r, and the projection here, this is x, and then this is your y. Okay. Suppose it makes an angle theta with respect to x-axis, and let us say the magnitude here is small r without an arrow. Okay. Then there is a relation between r, theta, and x and y. All of you know this. What is x? X is r cos theta, y is r sin theta. Now I will take this vector and then I will ask, suppose I make a rotation of these coordinate axes. Okay, then what happens to this vector? Okay, so first of all, you can define a vector like this, and also you can define it in terms of its components, right? Some people write it is like this, x, y. So once you know what are the components, if you, for example, if you know Vx, Vy, Vz, you know this vector V completely. It's specified in terms of its components. Similarly, if you know x and y, then you know what this vector is. For example, suppose somebody says this is your x value and this is your y value, then you just consider this and then join this point, this vector is determined. So given the components, you determine these vectors. But these components are dependent on what is the coordinate system that you use. Okay? It depends on what you call as your x-axis and what you call as your y-axis. So if you change your axis, okay, then the components will also change. For example, suppose I will perform a rotation. I will say this is my x-axis. So this is my old axis, but I have a new coordinate system. This is my new x-axis. I will call this to be x prime axis, and then this is my new y-axis, y prime. And this coordinate system is obtained from the old coordinate system by performing a rotation. So let's say I have rotated it by an angle alpha to find my new x-axis and y-axis. Then of course, obviously the component of this vector changes under rotation. Okay? This is going to be, I consider the same vector, but now this is going to be my x prime, this value. And this value here is going to be y prime. So what are the components of a vector? Basically depends on what is your coordinate system. And if you change your coordinate system, then the notion of the values of the components do change. But they don't change randomly. They change in a nice fashion. For example, because this angle here is alpha, although x, y are different from x prime, y prime, they are related to x and y in an interesting way. How are they related? X prime, x cos theta, x cos alpha, right? This angle is alpha. So this is x cos alpha minus y sin alpha, and y prime is equal to x sin alpha plus y cos alpha. This is a simple relation which you will be able to derive just from geometric consideration. Okay. So this is how these quantities are related among each other. And the same relation all of you are familiar with matrices, right? So I can write it as a matrix relation. I can say, I can represent this, the components of a vector. It is more convenient, instead of representing it by a row, it is more convenient to represent the components in terms of a column. So if I do that, then x prime, y prime are related to x and y by this: cos alpha minus sin alpha, sin alpha cos alpha times xy. So this is how the components of the position vector are related among each other. Okay. Now it is a simple exercise. You can show yourself. You consider any vector on a plane. Okay. So here we have derived it for position vector. That will also tell you how are the unit vectors related among each other. Okay. You can obtain the relationship between the unit vectors, and if you consider any vector on a plane v equal to vx x cap plus vy y cap, this is an exercise for you, okay? Then show that if you perform such a rotation, the components of this vector vx vy are related exactly the same way as the components of the position vector, okay? You consider any other vector, if you perform a rotation, then the components will be related by vx prime vy prime is equal to cos alpha minus sin alpha cos alpha times vx vy. So this is how it will be related, okay? You can obtain it any way, but a simple way is to consider this, and this is also because it's the same vector, this will be vx prime x prime plus vy prime y prime cap, where x prime cap and y prime cap are unit vectors along this direction. Then you know how x prime y prime and x cap y cap are related. From that relation you can simply derive this relation, okay? So this is how the components of a vector is given on a plane, okay? If you perform a rotation, then the components are related among each other. They change, but they change in a nice way, and this is how the new components are related with the old components. Now what about a vector in 3 dimensions? This is just we considered a vector in a plane, but the generalization to a vector in 3 dimensions is straightforward, it's trivial. If you consider 3 dimensions, then there are 3 independent ways you can perform a rotation. For example, you can keep the z-axis fixed and then you can rotate about the z-axis, okay? That is going to be exactly the same way, it's going to be this rotation. You can keep the y-axis fixed and then you can rotate the z-x plane, okay? So that will have a relation which will be something very similar to that. You can keep the z-axis, the x-axis fixed and y-z plane you can rotate, okay? So you can, these 3 rotations you can write it in a straightforward manner, x prime, y prime, z prime. Suppose I rotate about the yz plane, okay, by an angle gamma, okay? So what will it be if I rotate about the x-axis? The x value will not change, only the yz values they will mix among themselves. So that will be 1 0 0 0 0 cos gamma minus sin gamma cos gamma times x y z. So x prime will be x, y prime will be cos gamma y minus sin gamma z, z prime will be sin gamma y plus cos gamma z. This is how it will be. So so what is important is that in the case of a plane, there is one continuous parameter, and you consider any arbitrary rotation on a plane, okay, then that rotation can be described in terms of this parameter alpha. For different values of alpha, you have different rotations on a plane, okay? So there is a one parameter family of rotations on a plane. Yes?
Sir, but the 3-dimensional space can be rotated in another way as well, right? Sir, like not keeping one axis fixed, but all three changing.
Yeah,
Like if this is our plane and
absolutely.
that axis, and something like this.
So the claim is that I mean, here what we are doing is that we are fixing the origin. Okay, so we are keeping the origin fixed.
No, sir. Even the origin
Yeah.
is changing.
No, if you change the origin, then it's a different story. Okay.
Sir, like if this is the original 3D plane, and if I do it like this.
Yeah, you can change the origin. What I am saying is, if you do not shift the origin, then there are three independent ways. Okay, you can have an arbitrary rotation, but any arbitrary rotation in 3 dimension you consider, that can be described in terms of 3 parameters. Okay, on a plane there is 1 parameter, in 3 dimensions there are 3 parameters. So an arbitrary rotation consists of, it's basically in 3 dimensions, it's a 3 parameter family of transformations. Okay, on a plane it's just a 1 parameter family of transformations that describe rotation. Okay, and exactly this way, if you consider, so this is how the position vector transforms. But if you consider any arbitrary vector, under rotation it will transform exactly the way the position vector transforms. Okay, for example, if you consider a vector in 3 dimensions like Vx x cape plus Vy y cape plus Vz z cape, and suppose you rotate it by an angle gamma along the x-axis, then this is how the components will transform. Okay. Yes, there was a question from somewhere here. Okay. So this is how the components of a vector will transform. Okay. Now what we will do, so this is a qualitative argument. We can prove it in a more abstract way. Okay. How can we prove that there are 3 and only 3 parameters when you perform a arbitrary rotation and nothing else? Yes.
Sir, like the vector in 3D space can make angle alpha, beta, gamma with axes x, y, and z. So the rotation in any angle can be expressed in these 3 forms.
What is the question? I don't understand.
No, sir. You told no, like how to prove that if there are only 3 parameters in 3D space. So we can say after rotation there's angle alpha, beta, gamma with respect to the axes. So there will be only 3 parameters.
There are 3 parameters. Yeah. So basically, what you are saying is that because there are 3 axes, and you perform a rotation about x-axis, that's alpha, and you perform about y-axis, that's beta, that's gamma. But that's not a proof, right? Yes.
Sir, we can say that. So we can say that for a rotation, you need to first have an axis of rotation, not the x, y, z axis. So any line in 3 dimensions can be defined by 2 angles, one with one axis and another with a perpendicular axis. We don't need a third angle because using
Okay.
because two of them will be complementary. You can find the other one. So
Okay.
each line can be defined using 2 angles. So that defines your axis of rotation. And after that, you have to rotate about that axis through some other angle alpha. So you have 3 angles which will fully describe any rotation.
Good. Did you understand his argument? So what he is saying is that, suppose this is your x, y, z. Okay. So you consider any arbitrary direction. Okay. That direction can actually be obtained from this by 2 parameters. Okay. And about this direction you make a rotation, that is just one additional parameter. So there are altogether there are 3 parameters. There are some other question from there also. So but let's do it in a slightly more abstract way, because that is also going to help us in understanding something more. I will introduce a new notation. I will say x is x1, y is x2, and z is x3. Okay. So this x, y, z, I will represent it in terms of indices. I will say xi, and then I will say that I runs from 1 to 3. Then in 3 dimensions, I am just making some arbitrary rotation. So what will happen? x1, x, y, z will go to x prime, y prime, z prime. Okay. And so this is just some xi prime, right? And they are related among each other. How are they related? We don't know exactly how they are related. It depends, it's slightly more complicated. It's simple if I rotate it about x-axis or y-axis or z-axis. But as you are saying, if you just consider an arbitrary direction, it is not that simple. It is more complicated. But what is important is that no matter what it is, this is a linear transformation. In the sense, x prime, y prime, z primes, they all will be linear combinations of x, y, z. Okay. So I will say x prime is some r11 x plus r12 y plus r13 z. I don't know what are these r11, r12, r13. But there will be some R1, some constants R11, R12, R13 that will depend on what is the orientation of this direction with respect to x, y, z. But there will be some constant quantity, some constant coefficients. They are independent of x, y, z. So this is how it will be related. Or if I use this index notation, x1 prime is r11 x1 plus r12 x2 plus r13 x3. Now you see why I have introduced this index notation, because now it will be very straightforward for me to write it as some r1k xk, k is summed from 1 to 3. This is how it will be, right? Similarly, x2 prime will be some coefficients r21 x1, r22 x2, r23 x3. I don't know what the coefficients are, but I call these coefficients as r11 x1, r1, like that. So in general, so you will have so x2 prime will be some over k, r2k xk, and x3 prime will also be r3k xk, where k is summed from 1 to 3. And therefore, now you see all these 3 relations I can write it in a compact way, saying that xi prime is r I k xk sum over k, k equal to 1 to 3. in this notation, what is important here is that this index k is summed over from 1 to 3, whereas this index I is not summed. Okay? So therefore, this actually represents 3 equations. The value I takes 1, 2 and 3. If I equal to 1, I obtain this equation. If I equal to 2, I obtain this. If I equal to 3, I obtain this. This is just a more abstract way of writing this relation x1 prime, x2 prime, x3 prime is equal to R11, R12, R13, R21, R22 and so on and so forth. X1, X2, X3. So this relation is written in a compact way like this. Okay. Now, so let's write it. So suppose I call this column vector to be some x prime, okay, and I will call this matrix 3 by 3 matrix to be R, and this column vector to be x. So in matrix notation, I can write this way. So the same relation, I can write it like this explicitly, or in terms of indices, I can write it this way, or I can introduce 3 matrices. I can call this to be x prime, I can call this to be R, I can call this to be x, and then this is what I will get. But remember, so this is the most general linear transformation, okay, which relates the coordinates x prime, y prime, z prime with x, y, z. But we are not interested in an arbitrary linear transformation. We are interested in rotation. And what does the rotation do? Although the rotation, remember, it changes the components x, y, z, x prime, y prime, z, they are different. But if you look at the length of a vector, it remains unchanged. Okay? No matter which way you rotate, the length of a vector remains unchanged. So therefore, what is the length? It's just x square plus y square plus z square. So this quantity remains unchanged. In this sense, this will be same as x prime square plus y prime square plus z prime square. Okay? All right? So, but this quantity is nothing but, in matrix notation, this will be this x transpose x, and this will be x prime transpose x prime. All right? So this is how x prime and x are related. And if you look at x prime transpose x prime is this. So x prime transpose is Rx transpose, and x prime is Rx. So this will be x transpose R transpose Rx. And this quantity has to be same as x transpose x. If you do not want any restriction on the coordinates, then the only way it can satisfy, this relation can be satisfied, is if this quantity becomes identity. Okay? So this is the most general linear transformation, but this transformation will keep the length unchanged provided this quantity remains identity. Okay? R transpose R equal to identity. Okay. if you consider a matrix which satisfies this relation, it is called as an orthogonal matrix. Okay? So rotations are basically orthogonal transformations. But not all orthogonal transformations are rotations. Can anybody give me an example of a orthogonal transformation which is not rotation? Sorry? Huh? You just change one of the x's. Okay? But that will not be an orthogonal transformation. Yes.
Sir, reflection.
Very good. Reflection is an example of an orthogonal transformation which is not a rotation. Somebody was saying something.
So, adding some constant transposition.
This is the transposition, yeah.
Adding some constant, I mean.
Huh?
Adding some constant, moving the vector up or down.
Yeah, shifting origin, which we are considering transformations with a fixed origin. If you translate, then again that's a different story. We can talk about translations little later, but let's just consider a system where the origin is not changed. We are making all sorts of transformations, orthogonal transformations without changing the origin. So reflection is an example. So there are three ways you can reflect. You can say you can change x to minus x, or y to minus y, or z to minus z. Okay, but they are not independent. Okay, they will all be related to one another by rotations. So rotations and reflections are basically orthogonal transformations. There is nothing else. But the difference, there is a main difference between this transformation here and rotation. Rotation is a continuous transformation. Okay, you can just consider a parameter, and then from identity you can change this parameter slowly. You can obtain any finite rotation. But this is a discrete transformation. There is no continuous parameter associated with it, which you can slowly change and then you can obtain this release. Okay, so that is the most important difference. And from this relation, you can see, so there are two possibilities here. If you just take the determinant of this matrix, determinant of R, transpose determinant of R is just 1. And determinant of R transpose is same as determinant of R. So determinant of R square is 1. So determinant of R is plus or minus 1. And if you make a transformation like this, the matrix here is minus 1, 0, 0, 0, 1, 0, 0, 0, 1. Let's say you just consider x to minus x, y to y, z to z. This is a reflection, right? And the matrix R associated with this transformation is just this. Its determinant is minus 1. If you just do this, then this is the transformation. Its determinant is again minus 1. Okay. If you do two such reflections, then it is just a rotation. Okay. It is a rotation by, I mean, if you just look at the rotation matrix, you just take the angle to be pi, then you just get this this thing. Okay. So that's why all these three transformations are not independent from each other. Okay. So there is just one transformation, and then so you can just say this is the transformation. This is called as parity transformation. This is a discrete transformation, and this has determinant r minus 1. All others transformations which satisfy this have determinant r plus 1. Okay. And they are all rotations. And from here, from this relation, you can see why there are only 3 parameters. There are 3 parameters because if you just consider an arbitrary linear transformation, how many parameters it will contain? 9 parameters. Very good. So, but this is not arbitrary transformation. The transformation has to satisfy this relation. Okay. So suppose you have some 2 parameters, but they are related. So let's say alpha and beta are 2 parameters. But suppose there is an equation f alpha beta is equal to 0. Okay. Then these 2 parameters will not be independent, because there is a relation between them. There is an equation which they have to satisfy, and then you can eliminate by using this equation. You can eliminate one parameter. So therefore you will have only one independent parameter. Now this R has 9 parameters, but there is a matrix relation like this. So therefore you have to ask how many constraints this equation gives. Okay. How many constraints it gives? It doesn't give 9 constraints, although it's a matrix equation. You see this, it's symmetric. Okay. R transpose R is a symmetric matrix. If you take its transpose, it will again be R transpose R. So therefore this has something like A, B, C, B, D, E, C, E, F. It will be of this form, and this will be 1 0 0 0 1 0 0 0 1. So there are only 6 equations. Okay. So this says A equal to 1, B equal to 0, C equal to 0, D equal to 1, E equal to 0, F equal to 1. So this gives you 6 equations. There are 9 parameters here, but using these 6 equations, you can eliminate 6 parameters. So therefore there are only 3 parameters left, and those are the 3 independent rotations. So you can see that you cannot have any new parameter if you perform a rotation in 3 dimensions. So what we saw is the following. We saw that if we perform a rotation, then the components of the position vector transform this way, where this R is a orthogonal matrix. R transpose R is equal to identity. Okay. That is what is a rotation. That is what a rotation makes to the components of the position vector. Now what I claim is, if you consider an arbitrary vector Vi prime, okay, you consider not the position vector but any arbitrary vector, then under a rotation it will transform, the components of the vector will transform exactly the same way. It will go from Vi prime to sum over k equal to 1 to 3 r I k V k, where r I k are basically satisfying this relation. Now what I will do, I will turn it around and then I will say, instead of calling something with a direction and a magnitude as a vector, I will say, suppose I have a collection of 3 quantities, and if these 3 quantities transform this way under rotation, then these are vectors. Okay? So, now I am turning the definition around, and then I am saying that this is what makes a set of 3 quantities vector. Okay? Any set of 3 quantities which transform in this fashion under rotation are called as vectors. Now, what is the use? I started with the position vector, and then I said that if I perform a rotation, this is how it changes. Then I claimed that if you consider any arbitrary vector and make a rotation, this is how it transforms. This is also something simple to check. So, therefore, I saw that this is how the components transform. So, now I say that I will take this as the definition of my vector. I will say that if I have a collection of 3 quantities which transform this way under rotation, then I call them vectors. So, what is the use? What is the new thing that we are getting here? The new thing is the following. Okay? So, there are several new things. The first one is the following. Suppose you take the position vector, we saw that this transformation actually can either be rotation or it can be reflection. Okay? Reflection basically means I will call this to be parity. It is just another fancy name for reflection. It says it is a transformation which takes x to minus x, y to minus y, z to minus z. Such a transformation is called as parity transformation. Okay? And if you take the position vector, obviously under parity transformation, the components goes to minus themselves. Okay? Now, you take some vector v. Okay? Let us say the components under parity, if you make such a transformation, let us say the components go to minus of themselves. Okay? This transformation I will define it as parity. I will call this to be parity. Okay? And I will say, I will call, let us say A is a vector, AI's are its components. Under parity transformation, they go to minus AI. Okay. B is another vector. Its components are BJ's. Under parity transformation, they go to minus of themselves. Suppose I take 2 vectors. Okay. Under rotation, they transform exactly like the position vector. Under parity also, they transform exactly like parity vector. Okay. Now, you introduce a third vector C, which is the cross product of A and B. Okay. Now, I don't have any choice. Under parity, the components of A behave exactly like the components of position vector. The components of B behave exactly like the components of position vector. What about the components of C? Suppose Ck under parity, what happens to these components? Who can tell what happens? Let's say Cx, okay, Cx is Ay Bz minus Az By. What happens under parity? They will all be the same, okay? Very good. So these are called as pseudo vectors. Okay. So therefore, I have now by introducing this kind of notion, I can distinguish vectors among themselves, and then I call these to be the regular vectors or polar vectors, and these are called as pseudo vectors or axial vectors. Okay. And in physics, there is a classic example. If you consider electric field, then they are just the regular vectors. Okay. On the other hand, if you consider magnetic field, then it is a pseudo vector. Okay. But there are more general quantities you can introduce. Okay. So first of all, you can distinguish between vectors and pseudo vectors. Exactly the same way you can introduce the notion of a scalar and pseudo scalar. Okay. If you just consider A dot A, okay, under parity, it just goes to same A dot A. If you consider A dot B, where A and B both are polar vectors, it goes under parity as A dot B. On the other hand, if you have a pseudo vector, so let's say A is a regular vector, V is a pseudo vector, under parity it goes to minus A dot V. Okay, so if you take a rotation, if you make a rotation, then these quantities remain unchanged. On the other hand, if you make a parity transformation, they change their sign. So such quantities are called as pseudo scalars. So you have a pseudo vector, and similarly you have pseudo scalar. Okay. But what I want to introduce is that I want to introduce another new concept. So let us say A is a regular vector, okay? Its components are AI. Let us not worry about the parity transformation for the time being. Okay, let us just consider a simple orthogonal transformation, which is a rotation. So let's say AI is some vector, Bj is another vector. Now I will consider the collection of all such numbers. So how many numbers are there? Yeah, I and J runs from 1 to 3. So there are 9 obviously, right? So how do these quantities transfer? They do not transform this way, because AI goes to AI prime, which is sum over K, or let's call sum over P, R of IP, AP. Okay. Bj's, they go to Bj prime, which is sum over Q, R, JQ, BQ. Okay. Now suppose I call this to be some Tij, okay. Tij is equal to Aibj. So there are 9 such quantities. Now if you make a rotation, they will not transform this way, okay. The transformation is more complicated, but it is still a nice transformation rule, okay. How do they transform? T prime ij, Tij goes to T prime ij, which is Ai prime Bj prime, and this quantity is Rip Rjq and APBQ, which is RIP RJQ TPQ. Okay. So this is how these quantities transform. This is an example of a set of quantities which under rotation transforms this way. Okay. And these quantities, yes, what is it? Yeah, summation. Thank you. So there is a sum over P and Q. There is a sum over P and Q, which runs from 1 to 3. So these quantities are called as tensors. Okay. This is an example of what are called as tensors. Under rotation, if you have a set of, let's say, 9 quantities which transform this way, then they are called as tensors. Okay. And what is important to note here is that there are 2 R's here. Okay. If you have 2 R's, then you call this to be a tensor of rank 2. Okay. Depending on how many R's you have in the transformation rule, you call these quantities to be tensors of rank that. So in that sense, if you consider a vector, it is just a tensor of rank 1, and if you consider a scalar, it is a tensor of rank 0. Okay. And these are basically tensors under rotation. I am considering the coordinate transformation here, which is a rotation. And I have these set of quantities which under rotation they transform in a nice fashion, and these quantities are basically tensors. And please remember, although I have started with something which is of this form, not all tensors can be expressed like this. Okay. For example, I will give you one example. Okay. You consider a matrix so this is because it has 2 legs here, it can be represented by a 3 by 3 matrix. So you call let's say M is a matrix whose components are xi, xj. Okay. So what is M? M is x square, xy, xz, xy, y square, and yz, xz, yz, z square. This is a tensor. Okay. It's given I mean, it's very obvious that if you make a coordinate transformation, then the components of M will transform this way. And it is written this way. But you consider, let's say some M tilde, okay, which is M minus trace of M. Okay, trace is some quantity which does not change under rotation. Okay, so you just introduce this. Because this is invariant, this quantity will also, if you consider its components Mij, under a rotation, the components of Mij will also transform exactly this way. But M tilde cannot be expressible like this. You cannot write it in this form. So not all tensors can be expressible in this way. Okay. What distinguishes them from the regular ones is that the transformation rule. If you have a nice transformation rule like this, then you call this to be a tensor. Now in physics, why they are important? They are important because of this thing, okay? So because of this relation T prime Ij is equal to Rip Rjq Tpq. So why is this transformation rule important? It is important because suppose the components of a tensor vanish in one particular coordinate system. Okay. If they become 0 in a particular coordinate system, then they will be 0 in all coordinate system. Okay. You make all possible rotations, they will still be 0. Equivalently, if you have a tensor equation, then the form of this equation will remain the same in all coordinates, all orthogonal coordinates. Okay. That is a very, very important principle, and this is what is called as the principle of relativity. It tells you that if you want to formulate the laws of nature, then the laws of nature must have the same form in all orthogonal coordinate systems. If you make an orthogonal transformation, then the equations of motion should look the same. And that tells you that if you want to write down the laws of nature, then they must be expressible in terms of tensor equations. Okay? And this is much more general than orthogonal transformation. It is the same principle that that led Einstein to formulate his special relativity. It is the same principle that led Einstein to formulate his general relativity as well. And what is the difference is that the difference is this transformation. Okay. So far I am focusing only on rotation, orthogonal transformations. But you can have more general transformation that we will discuss after the break. We can have transformations which are not orthogonal transformations, that are more general transformations. They have more interesting properties. And you can define tensors under such transformations. And you can say that the equations that you write down should actually be expressible as tensor equations under that particular transformation. That is that actually provides a very serious constraint on what kind of equations you can write down. Okay. And then that is how then what Einstein has realized is that if you just consider, let's say, Newton's laws of motion, then they are not consistent with a particular set of transformations. They cannot be expressible as tensor equations under a certain class of transformations which are called as Lorentz transformations. Then he said Lorentz transformation is a more fundamental transformation, and any set of laws that describe the nature must respect this transformation. And because Newton's laws do not respect these transformations, so they can only be an approximation to a more fundamental set of equations which respect these transformations. That's how he formulated his special relativity. Okay, so I think we will take a 5 minutes break or so, and then we will again resume.